Welcome students to our last module of operation research. It is the module 7. It says we have two parts in this particular module, and the two parts are, first part is nonlinear programming, and the second part, or the last part you can say, is the dynamic programming. Okay, so as because we have came to the last session of operation research, let us review some of the important terms associated with operation research, and gradually we will move to the nonlinear programming, the study of nonlinear programming, the difference between a nonlinear programming and linear programming, and gradually we will see the formulation and the structure, and next we will see some characteristics of nonlinear programming. So this is whole about the topic of our today's video session. So kindly watch the video till the end. Hope you will enjoy the session. Okay, so starting with this particular last topic or module of our operation research, I must tell you, in this operation research we are dealing with optimization. The foremost word, or I say the most important matter or the topic, is the optimization. We are doing here optimization. Okay, so if someone asks you what is optimization, you have to tell that optimization is the act of obtaining the best result under given circumstances. Now these circumstances you know already, these are the constants. We used to say in our linear programming or non-linear programming, we used to say these circumstances as constants. Okay, now in design, construction, these are the fields: design, construction, maintenance, you can say. So of maintenance of many engineering system, engineers have to take many technological and managerial decisions at several stages and under some given circumstances. So the ultimate goal of such decisions is either to minimize, you already know these things, just to remind you, I am having a small session first, then we will proceed to the non-linear programming. So ultimate goal of these all decisions, or all these decisions, is either to minimize the effort required or to maximize the desired benefit or profit, you can say. Okay, since this effort required or the benefit desired in any practical situation can be expressed as a function, we already know how it is expressed, x1, x2, already know these things. It can be expressed as a function of certain decision variables. These are the decision variables you already know. Optimization, this optimization can be defined as the process of finding the conditions that give the maximum or minimum value of this particular function. Okay, now I must tell you, you already know actually, but I must draw you a diagram which will make your concept much more clear. In minimization problem, where we founded the dual of the primal solution, what we have founded actually, that I will show in a graphical way, which will help you to remember more easily. Say this is x and this is fx. Okay, we have a graph. Now you can see, let us say this one, and so this one. Okay, so say this one is the fx, and say this one is the x star value. Okay, x star, it is optimal, you can say. Okay, say this one is the minimum value. Okay, so minimum of fx we have found here. Now this mirror image, you already know what is mirror image. We already done a session over this particular minimization and duality problem, and if you haven't seen that video, you can see in my playlist. Okay, now this one, it gives you minus of f of x. Okay, so you can see this is the mirror. Now you can tell that this extra value in this quadrant, it says the maximum of minus f of x. Okay, so you know the minimum value in a particular quadrant gives you the maximum value, just mirror image in the different, or you can say in the opposite quadrant of that particular function. Okay, so minimum of fx gives you maximum of minus fx in fourth quadrant. Say this is the first quadrant and this is the fourth quadrant, so you can have the minimum and maximum values. Okay, consequently, now these mathematical programming techniques are very useful in finding the minimum of a function of several variables under a prescribed set of constraints. You already know constraints are these things. Okay, now let us discuss on some history or development of operation research. Okay, the existence of particular this optimization techniques can be traced from the days of Newton, Lagrange and Cauchy. Okay, from their time only this optimization methods existed. Okay, but after the Second World War, this particular operation research when came into existence, or you can say there was much need of operation research during the Second World War, this became most popular one. Okay, now the development of differential calculus methods of optimization was possible because of the contribution of mainly Newton, Leibniz, and another scientist was there. His name was Leibniz. Now later you can say the development of simplex method. We have already done the simplex method. How to solve, we know how to solve simplex method in linear programming. Okay, the simplex method was developed by Dantich in 1947. Okay, and it was for linear programming, you already know, and the enunciation of the principle of optimality, that we will be having a session of optimality in dynamic programming in the coming session of my videos. So principle of optimality in 1957, we already have this in our syllabus only. Okay, was developed by Bellman. This is for dynamic programming problem. Okay, now Kahn and Tucker are also very famous. Kahn and Tucker in 1951. Okay, they worked on the necessary and sufficiency conditions for the optimal solution of programming problems, and that laid the foundation of great deal of later research in nonlinear. There are much more contributions in this particular nonlinear programming. Okay, and one more scientist was there, mainly two was there, Jyotenjit and Rosen. They also contributed a lot in nonlinear programming. Okay, so I'm just telling you this in small, the history and background of this particular thing, as because this is very important, not from the semester, maybe they are not going to ask you in semester examinations, but as an engineer you must know when you are going to join a company or become a manager, you have to take managerial decisions, or in some interviews they can easily ask you question, can you name the person who developed this simplex method which you have applied to solve linear programming problems. So what was the year? Can you tell maybe there may be question, but since this is in your syllabus, you must know the at least the name of the scientist who developed this particular simplex method. Okay, so this is all, you can say, a brief introduction or background of optimization techniques. Okay, so let us now come to the direct section of nonlinear programming, where we will see what are the main things behind this development of nonlinear programming from linear programming. Okay, so coming to this particular nonlinear programming, there are, first we will study why study NLP. Okay, that is nonlinear programming. Why should we study? What are the reasons behind this NLP? First, I can chalk out some important criteria. There are many reasons, but I can write you some basic ones. Say this linearity assumption. Okay, first is the linearity assumptions. What does this means actually, linearity assumptions? Look, in LP, we assume all are in a linear one. The objective function, you can say this is the objective function. Okay, say z equal to maximize or minimize, whatever you can say. Maximize z equals to 5x1 plus 3x2, say. Okay, subject to take any constant, 4x1 plus 3x2 can be less than or equal to 4, or whatever you can take. So you can see in linearity problems, what we are assuming that all the objective functions as well as the constant functions, constants are in linear. They are linear. Okay, but what happens in actually what we are dealing? We are dealing with the real problems, no? We are dealing with the real world problems. So this linearity may somewhat become not valid, you can say. Okay, in some of the in real world problems, what happens in real world, this may become square one, or this may become a root one. Okay, so linearity becomes not invalid in, you can say, in real world problems. So first assumptions, that is the linearity assumptions. Okay, that sometimes becomes invalid. Okay, so coming to the next point, I can tell you that second point is our additivity assumption. Okay, so first is our linearity assumption, second is our additivity assumption, third is our constant return. I will describe each and every one. Let us write first. Fourth one is efficient, you can say, efficient algorithms to solve NLPs. Now, first one I have already discussed, that is the linearity assumption may become invalid in some of the real world problems. Now, the second one says the additivity assumption. We generally, what we do, we generally used to have us say this one, say we have M1 machine and M2 machine. Okay, say we are having, and here we are having, say availability is 4, you can say. Okay, so what we do actually, sorry, this one will be, this one say P1 and this one say P2, this one P1 product and this one P2 product, and say this one M1 and this one M2 machines. Okay, say this is 4 and this is 3, and their availabilities are 4 and 8, say. Okay, so what we do actually, we take and say there are profit given as 3 and 5 rupees, say. Okay, now during formulation, what we do, we just take as x1 unit of P1 and x2 unit of P2. And what we do, we construct the objective function as 3x1 plus 5x2. We just simply add total profit. We just simply add 3x1 plus 5x2. Okay. And for the constants, we used to just multiply 3x1 plus 4x2 and say less than equal to 4 we used to give. And for this one, 4x1 plus 3x2, this one equal to 8, and x1, x2 greater than equal to. This is the formulation or structure of a, you can say, given LPP problem. Say a random example I have taken. Okay. Now let us speak about this particular profit. This profit gives tells you that if we manufacture a single unit we have of P1, we are having a profit of 3 rupees, and if we are manufacturing a single unit of P2 product, we are having a profit of say rupees 5. Now the total profit we used to add, just simply add, that is 3x1 plus 5x2. But again, if we come to the real life problems or real world problems, okay, this sometimes this simple addition of 3x1 and 5x2 becomes invalid one. Why? As because say, why we are multiplying with 3, for unit product of production of P1 we are having 3 rupees of profit. But say we are having x1 amount of P1, then we are having 3 into x1 amount of profit. But this 3 into x1 sometimes becomes invalid in real world problems. For say, if we are manufacturing one product, we are having 3 rupees of profit. But manufacturing 3 product or 300 product or 3000 product, we may have more than 3000 into x1 amount of profit. You are getting what I am saying? Say we are having x1 product and we are getting 3x1 profit. As because for per unit, for 1 unit of product, we are having 3 rupees of profit. But this 3 into x1 gives you the total profit. But this may not be valid in some of the real life problems. Say when we are going to a shop and we are buying a lot amount of products, then the shopkeepers or the distributor giving you a huge amount of discount. Say when you are buying 30 pieces of say pen, they are selling it at rupees say 100. Okay, but for 60 pen they are giving you selling it at 180 rupees. It should be have 200, but you are getting 20%, 20 rupees as discount. So in real world problems, you can say we are manufacturing a single unit of product and we are having a 33 amount of profit. But say we are manufacturing 3000 of unit of product. We cannot simply multiply 3000 into 3 and we are getting the profit. We cannot. This sometimes becomes invalid in real world problems. The profit may be larger than 9000. Say the profit can be of 9500 only. Okay. So just simply adding up the profits does not valid in some of the real life problems. That is the second assumption we are taking in solving linearity problems. So there may be a non-linearity. Okay. Now come to the third point, which says constant return to scale. What does that mean actually? This constant return to scale actually means actually additivity and constant return to scale somewhat I explained in a single problem actually. Additivity says you cannot simply add, that is 3x1 plus 5x2. You cannot simply just add these two profits. Sometimes in real world problems that may this one profit and this one profit cannot be taken into additive one. Okay, this one may be a different thing. This one, say this one profit is for your products, this one for your saving of electric bill or saving of salaries or something different from this. You cannot just simply add. This may be different, x1 and x2 maybe some different things. Okay, So you cannot just simply add this one. Okay, now this constant return to scale that I already told you, that for unit profit we are having, say, 3 rupees of profit, and when we are manufacturing x1 amount quantity of profit, we are just simply multiplying it with 3x1. That gives you the total profit. That's that. But that this thing says, this constant return to scale says, this doesn't always have to be this way. That means if you are having 3 rupees of profit and you are manufacturing x1 amount of quantity of product, you just cannot simply multiply 3 into x1. Okay, that may be maybe in a different form. Okay, that may be larger than 3x1. Okay, maybe it can be like this one also, 3x1 plus 2 or 3x1 plus 3 also. Okay, so these are the things. The last one, you can say, we have developed efficient algorithms to solve NLPs, and NLPs is the, NLP, nonlinear programming, is very much important in solving real-day problems also, as because in real-day problems or real-world problems we are facing much more the decision variables in non-linear type, say x1 square or x into y. We are having this kind of things only, okay, in our real-day problems or real-world problems. Okay, that's why non-linear programming gained its popularity and came into being. Now, let us have a simple graphical illustration of linearity problem and non-linearity problem side by side. Okay, let us see. We are having say a linear programming. Okay, in linear programming, if you solve a graphical, a linear program in graphical way, say you are having this kind of graph. Say, for example, for the time being, okay, say we are having this type of problem, and these are, you already know, I have given a video of how to solve linear problem with graphical. You already know how to find the the next step is to find the feasible region. Say this one is towards the graph, this one is the origin. Say these lines, these are the constants, this represents the constants, and these constants are less than equal to, say this is a maximization problem, and these are the less than. So less than equal to means the direction is towards the origin. Say this one also is less than equal to, so this is also towards the origin. Now the feasible region, you can see over here, this one is the bounded or feasible region, you can say. So these are the corner points. So you already know how to solve this LP problem using graphical method. Now let us take a sneak peek on the non-linear programming problems. Okay, say we have a problem like say this one, maximize z x into y, I can say. Okay, subject to for x plus y less than equal to 8. Okay, and x should be greater than equal to 0, and y should also be greater than equal to 0. Now look, this is the constant, and the constant is, you can say, this linear one. Okay, you can say this is linear one. But if you can see the objective function, this says x into y, which is not a linear one. This is a non-linear objective function, you can see over here. Okay, so this type of problems we are facing in our real life problems. Okay, real world problems. So now how to solve this, or how to construct this? If you construct this particular graph, or I can say say a rough graph I can draw for you. Okay, say this one, say this is the x and this is the y. If you draw, or if you construct this particular graph, say this one and somewhat like this one. Okay, now this one is xy equal to 1, and this one will be xy equal to, say, 2. Okay, now if I draw another graph, say this one and this one, this will be the intersection point. Okay, where we will be having the optimal solution. Say, for example, okay, I am taking just example to give you a brief idea on nonlinear programming. Okay, so this is the optimal point we are having, and this is y x equals to 1, say y equal to 4. Okay, and this is the x y equal to 4 line. Okay, and this one is 4x plus y equal to 8, you can say. Okay, such like that. So you just stick to the concept of nonlinear programming, solving with graphical way. Okay, so you can see there is not such this type of feasible region, or you can say corner points which we have already defined in solving linear programming. For this nonlinear programming, we just having a intersection point over here, these curves. Okay, this curves almost looks like a hyperbola type. So this is the point of intersection where we are having the optimal point, say x1 equal to 1 and y equal to 4 for this particular objective functions. Okay, so you can see this is a basic difference of a graphical solution of linear programming and nonlinear programming as well. Now if we come to the applications portions, where do we actually apply applications of NLP, I can say, nonlinear programming. There are various fields. You can say it is applicable to all problems wherever we can encounter non-linearity. It is a simple way to tell the application, but in a broader sense, we are applying NLP in different sectors. You can say design of aircraft. Okay, or I can give you a more specific example. Say we have a pulley. Say this is a shaft and it is having a varying diameter. Okay, now if we try to solve this particular shaft having different, or you can say stepped, or you can say varying diameter, then we are having formula of cross section as pi by 4 d square. So this is d1 square, we have to add again pi by 4 d2 square. Okay, so you can see the square terms are coming over here. This is a real type problem I am showing you. Okay, I am giving just you an example. So in order to say, we have to add this one. Okay, this area of this one, cross section area of this one and this one. So you can see we are having this square terms. So this type of formulations are generally known as the non-linear type, as because we are not having the decision variables in a linear as the linear one. We are having decision variables in a non-linear manner. Okay, so you can say many fields are there where we apply non-linear programming, mainly design of aircraft, you can say aerospace structures, for minimum weight, you can say, and also there are optimal trajectories of space vehicles, you can say. Okay, and in civil engineering also they are using a design of civil engineering structures such as frames, you can say. Okay, frames, foundations, okay, towers, chimneys, you can also say chimneys. So okay, dams for minimum cost. Okay, and next comes to the minimum weight design of structure for earthquake, wind, and many other things, like design of water resources system for maximum benefit. Okay, optimal plastic design of structure, you can say. Okay, now coming to the mechanical components, you can say optimal design of linkages, you can say. Okay, cams, we have many more other things also. Gears, we are also having machine tools. Okay, and now in pumps we are also using NLP. Okay, turbines, heat transfer equipment for maximum efficiency, for motors also, generators, transformers. And coming to the dynamic problem is somewhat also related to this, and NLP will be having a dynamic programming, concept of dynamic programming in our latter part of the video. before going to the dynamic programming, I'll just let you know what are the different aspects or applications of dynamic programming. In dynamic programming, we have to find the shortest route taken by a salesman or salesperson visiting various cities during one tour. That was also a part of nonlinear programming also. So this all things you can see, there are various different applications of NLP, and there are various other fields where we can apply NLP to get a optimized or best solution, you can say. And now I will give you a different classifications, you can say, better, of NLP. Let us see what are the different classifications of NLP. Say this is the NLP, and we are having like this. We are going to solve also, unconstrained optimization and say constraint optimization. And in the second part, you can say this is will be convex programming, and we will be having non-convex programming also. Okay. Now in unconstrained optimization, we are having two mainly different techniques we are having in our syllabus. That is the direct search method, and the second one is steepest descent method. And under constraint optimization, we are having only Lagrangian multipliers. Okay, so this is the classification of different NLP problems. Okay, now if you take a look on this particular two types of problems we are having. One is the unconstrained optimization one and the second one is the constraint optimization. In the unconstrained optimization, as you can see, objective function is nonlinear. As you can see, this is a nonlinear. There are into terms and square terms as well. Okay, so it cannot be treated as a linear one. If it had been a linear one, then that particular objective function wouldn't having these terms. Okay, that is the square terms or multipliers. It will be a simple linear one. That is a 2x1 or 2x1 plus 2x2 or 2x1 plus x2 you can write. That is the linear one. And this one, when we are having the square terms or into terms, that is the non-linear one. Okay, so objective function is non-linear one here for unconstrained optimization, and there are no functional constraints as because it is unconstrained. That means we are having no constraints over here. So this is simple maximization f x1 x2, that is the objective function, and we are having no constraints. Simply this has this particular objective functions you have to maximize only. Okay, that is the unconstrained optimization. We'll be having this constraint optimization in our coming topics on coming video sessions on a particular direct search method, grid search method. There are different methods for solving this unconstrained optimization method, and you can also have a look on this one also. This is having three decision variables x1, x2 and x3, and this is also a unconstrained and non-linear type of programming or objective function. You can see x1 square, it is having a square term, and then into term x1 into 1 minus x2 plus x2 square minus x2 into x3 plus x3 square plus x3 is over also here. So you can see this type of things where they are having a square term or into term, and also no constraints are there. So this particular objective functions you can say as a non-constant optimization. Okay, now coming to this particular constant optimization type, we have some examples for you. Say this is a minimization of function fx, and this is also square terms are over here, 2x1 square plus 2x2 square, say 2x1 square plus x2 square. Okay, this is x2. Okay, I can write it once more. This is x2. So you can see over here that minimization of fx is 2x1 square plus x2 square subject to x1 plus x2. Look, this constant is not, you know, in non-linear type. It can be say as linear type. Okay, but if any one of this, either of these you know, objective function, or you can say constant equations are in form of nonlinear, you can say easily as a nonlinear type of programming we have to perform on this particular equations. Okay, so although it has a you know, constant equation as a linear type, but its objective function, that is a minimization of fx, is of non-linear type. This is non-linear type. I can write it over here as non-linear type. Okay, so you can see these are the examples. The next example says the maximization problem. Here it gives a maximization problem where fx is somewhat like ln. They have given ln. So different types of, you know, algebraic functions are coming over here in this. You can see there are different algebraic equations they are giving in a non-linear type. Okay, so this particular says objective function has to maximize fx, and it is given as ln. So it is a logarithmic function, you know, ln x1 plus 1 plus x2, and subject to 2x1 plus x2 less than or equal to 3, where x1 and x2 should be greater than or equal to 0. So you can see these type of problems are generally known as you know, non-linear type of programming. Okay, so let us have an idea of, you know, how to plot this non-linear type of programming. A simple idea. So if you plot these two objective functions, one is of unconstant type. Look, this gives fx1 x2 equal to 2x1 plus 2x1 x2 minus x1 square minus 2x2 square. This is of unconstant type, you can see over here, and this is of, you know, 2x1 square plus 2x2 is the objective function, and the constants are of linear type. But this is also a non-linear, you know, programming, you can say, as because the objective function is of non-linear type, that is 2x1 square plus x2 square, and it is subject to, you can write it as subject to the constants as x1 plus x2 equal to 1, and x1 x2 should be, you know, greater than or equal to 0. Now if you plot this one in, say, you will have a graphic you know, 3D type of view like this one. I will try to draw it in this way. Okay, it will somewhat like in this one, and this one, and this will go in the this one curve. Okay, so you know, this will be your feasible region for this particular unconstant type non-linear programming, you can say as. Okay, so this somewhat looks like this one. Okay, now if you plot this, you know, I can write it as a, you know, this is a 2, and this is plus 2, this is 1 minus 8, you know, and this is minus 6, you know. This type of graph you will get, okay, when you will try to plot this one type of unconstant type non-linear, you know, programming. Now if you plot this one with having this objective function and having constants equation, and you will get like this one only, like this one and this one, and you know, this will come over here as this one and this one. Okay, this will touch here. Okay, now the object you know, the feasible region will somewhat like this, enclosed in a envelope. Okay, so this one will be your feasible region, you can say. Okay, now you can also grade this one as, you know, 0 1 like this one, 0.5. okay, and this should be 0, 0. okay, this should be 0.2. okay, this should be 0.4, and so on, 0.6, 0.8 like this one. And in this side also you will getting this one amount of value, say 0.5, then 1, and then you are having 1.5, and then you are having 2, then 2.5, like this one. Okay, so you can just have an idea of how will this type of graph. In linear one, you have already seen the type of graphs in graphical solution. That was more like a in a simple way, like this one and this one, and this will be the feasible region. But in this type of where we are having the square terms and into terms, this one into terms we are having, in this type of non-linear type we are having this much type of feasible region. Okay. So this you can say as xy plane also, you can say. Okay, now this is the class on the introduction of nonlinear type of programming. So I'll stop just over here only, as because in the next session I will be giving you a much more clear idea on how to plot a graph using these equations, objective functions, as well as constant equations. So I think today is all about this particular the background of NLP, the formulation, what are the constant type, what are the non-constant type of nonlinear type of programming, how the graphs look like actually. Okay, so in the next video I will show you how to plot this actually the graphs, and we'll have some more fun in the video. Okay, so hope you have enjoyed in this session. Please share it with your friends. Please subscribe to my channel and stick with us for more updates on the videos. Thank you for watching.